Okay, let's jump right in. We're about to hack one of the most dreaded chapters in all of JE main chemistry, hydrocarbons. Seriously, forget trying to memorize a million different reactions. Today, we're building a game plan to absolutely conquer this topic and turn it into a source of easy, guaranteed marks.
Does this chapter just feel like a total maze? You know, with all these confusing rules, all these weird exceptions, and reactions that somehow look exactly the same when you're under pressure in an exam? Yeah, you're not alone. It's actually designed to be tricky, but that's exactly why we're gonna break it down.
So, we're not going to study this chapter in the old-fashioned way. Nope, we are going to decode it. Think of this as your insider's guide. We're going to learn to think like the people who actually set the questions, spot their traps from a mile away, and use some simple, really powerful shortcuts to solve these problems way faster than you ever thought you could. So here's our game plan. First, we'll size up the challenge. Then we'll build our core toolkit of the absolute must-know rules. After that, we'll learn how to dodge the most common traps, arm ourselves with some killer shortcuts, and finally, master the patterns that show up on the exam over and over again. Let's do this.
Okay, first things first. What is the actual challenge here? It's not just about knowing the reactions. The real challenge is that this whole chapter is just loaded with these subtle rules and little exceptions that are put there specifically to trip you up in a high-pressure exam. So just recognizing these traps, that's step one to beating them. All right, we know the problem, so let's build our solution. Before we even get to the cool hacks and shortcuts, we need our essential toolkit. These are the absolute, non-negotiable fundamentals. If you can master just these few core ideas, trust me, you've already won half the battle.
First up, the absolute basics. You have got to know these cold. It's like the alphabet. Alkanes, CnH2n plus 2, totally saturated. Alkenes, CnH2n, got that double bond. And alkynes, CnH2n minus 2 with a triple bond. Simple. This is the basic language we're going to be speaking.
Now pay attention here, because this slide covers a huge chunk of all addition reaction questions. The Markovnikov rule is super easy to remember. The rich get richer. The hydrogen atom just goes to the carbon that already has more hydrogens. Easy. Now, anti-Markovnikov is the exact opposite. And this is so important, it only happens under a very specific condition, which we'll talk about in just a minute.
This right here, this is a guaranteed question area. When you reduce an alkyne, the reagent you use literally decides the 3D shape of your product. If you see Lindlar's catalyst, the answer is always the cis-alkene. Always. If you see sodium in liquid ammonia, that's the Birch reduction. The answer is always the transalkene. There are no exceptions. This is easy marks.
All right, toolkit is ready. Now it's time for some defensive strategy. We're going to look at the most common traps that the JEE main sets for students, year after year. Seriously, knowing these is like having the answers to the test before you even walk into the room. Okay, so remember that special condition for anti-Markovnikov's rule we mentioned? This is it. It's called the peroxide effect. And listen closely. It only works with HBr. That's it. They will try to trick you. They'll give you HCl with peroxide or HI with peroxide. It is a classic trap. Don't fall for it. Anti-Markovnikov with peroxide is an HBr-only club. And here's another huge trap, the Wurtz reaction. Look, it's great if you want to make a symmetrical alkane from two identical pieces. But the second you try to use two different alkyl halides, it's a disaster. You get this messy mix of three different products. So if you're trying to build an unsymmetrical alkane, the Wurtz reaction is a total failure. And here are a few more rapid-fire traps to watch out for. With ozonolysis, you have to check the second step. Is it reductive, with zinc? That gives you aldehydes and ketones. Or is it oxidative? Because that will turn any aldehydes into carboxylic acids. That one little detail changes the whole answer. Next, stability. Just remember, conjugated alkenes with those alternating double single bonds are way more stable. For bromination, the main product always comes from the most stable free radical, so the tertiary position is your prime target. And a simple one to finish us off. Hydrogenation just adds hydrogen. It never changes the carbon skeleton underneath. Okay, defense is solid. Time to switch to offense. These are the shortcuts, the mental hacks that are going to let you solve problems in seconds. This is how you save precious time for the harder questions and lock in those marks. Oh, this trick is fantastic. For ozonolysis, forget the mechanism. Just find the double bond, take your mental pencil, and just erase it. And then just stick a double-bonded oxygen onto each of the 2 carbons you just split apart. That's it. Done. You have your products in like 5 seconds. It's that easy.
And here it is, the 1-second memory rule. You have to burn this into your brain. You see Lindlar? The answer is cis. You see Na-NH3? The answer is trans. This single rule solves any alkyne reduction question instantly. Okay, let's put it all together now. We've got the tools, we know the traps, we've got the shortcuts. Now it's time to apply everything to the kinds of questions that you are almost guaranteed to see on your exam.
This table right here, this is the master key to so many questions. Do you see the pattern? It doesn't matter if we're talking about carbocations, free radicals, or even alkenes. The trend is always the same. More substitution means more stability. Tertiary is better than secondary, which is better than primary. If you just get this one idea down, you can predict the major product in tons of different reactions, really fast.
This chart shows a really important inverse relationship. It's simple. The more stable an alkene is, the less energy it has packed inside. So when you add hydrogen to it, it releases less heat. A less stable alkene has more energy to give off. So get this. If a question asks which alkene has the lowest heat of hydrogenation, it's really just a sneaky way of asking which alkene is the most stable. So here's your final checklist for solving problems in under 20 seconds. For any stability question, just check for hyperconjugation or resonance. The more you have, the more stable it is. For ozonolysis puzzles, especially when they give you the products, just work backward with our eraser trick. Foolproof. When you're adding something like HBr, stop and think, is there peroxide? That makes it anti-Markovnikov. But even more important, can the carbocation rearrange to become more stable? That's a huge trap. And finally, aromaticity checks are free points. Is it a ring? Is it flat? Conjugated? Does it have 4n+2 pi electrons? If yes, it's aromatic. Don't. All right, let's do a final super fast recap of the absolute highest yield topics. You have to master identifying ozonolysis products. You have to know how to find the major product in halogenation by looking for the most stable radical. And you always have to watch out for carbocation rearrangements. Aromaticity problems, those are free marks. And never, ever forget that the peroxide trap only works with HBr.
So there you have it. After this quick breakdown, you have the tools, you have the strategies, and you have the shortcuts. You're not just studying hydrocarbons anymore. You are fully equipped to hack them. So the question isn't, can I survive this chapter? The real question is, are you ready to make hydrocarbons your scoring advantage on the JEE main? You've totally got this.